Yeah, can you hear me now?
Yep, perfect.
Yeah. So let me share my screen. So I'll be talking about some of the examples where we use the system profiling tools like the Nvidia profilers to better understand what's happening beneath you're running this model on the hardware. Um, okay, so I'm sharing my screen here. Okay, so if you go to this the repo and section 4, so we have this folder called as Nvidia Profiler. So here we have some of the examples of how can we use the Nvidia Profiler tools to profile a code. So for example, we have chosen the TensorFlow 2 CFAR 10.py that is in the first section of distributed examples. So we're just using the same examples and we're trying to um, try this out on the data GPU. So, so let me go to a quick brief overview. So NVIDIA has this tools called as Insight Systems and Insight Compute. So these tools are used to profile an application running on the GPUs. So previously there was a tool called as NVProp, like NVIDIA Profiler, but so this is the Insight family of toolkit is much a newer and more comprehensive profiling tools that NVIDIA is pushing out. Um, so, so the primary difference between the Insight systems and compute is that like Insight systems focuses most on the system-wide tuning. So it gives you information on what are the tasks that are running on the CPU versus GPU. And in terms of the GPU, so when you're running your code, how does that code runs on a GPU? So it gives you a list of kernels that are actually executing on the GPU. So this is a kind of a more high-level picture that you get using Insight systems. Whereas Insight compute is primarily focused on uh, you're optimizing the CUDA kernels, and it's more detailed information. So like what Taylor mentioned earlier, so TensorFlow Profiler gives you more information from the framework point of view. So the advantage with using the NVIDIA tools is that you get more underlying low-level information as well if you like to use that information to analyze your code and for its performance. So in this in this repo, so you have this script called as submit theta.gpu. That script actually has all the instructions to run the profiling code. So I'll go to that in a moment. So when you're running this Insight systems, so the way which you use is you use this command line option like nsys profile, and you pass your parameters. So here if you're trying to, if my code is called as myapp.py, so I just use this command line like nsys profile, and you pass those parameters along with your application. So once this code is run, it generates a file format called as QDrep. So that's kind of an internal representation which has all this profiling information embedded into that file. So there are two ways to do that. So one is by running this as a default as is, so you get this .qdrep files and a bunch of SQL database files. So what we can do is we copy that QDrep file to the local machine, and you have this tools called as NVIDIA Insight UI. That's NVIDIA Insight tools. So you can just copy that profile information to your local system and then import this profile and view the analysis. Or the other way is also to use this SSH tunneling, where you do this the forwarding onto on the data GPU. But having said that, it's kinds of adds sort of overhead. So it's better recommended to um, use the script to generate the profile on the compute nodes and then copy or SCP your data back to your local machine and view the analysis. So for the Insight system, so if you see the script here, so here we are using a container here. So we're using the TensorFlow 2 container. And the other thing is that we have to set the associated, the library path for the tools to read the interface to get those metrics on all the counter values. So here in line 15, so we are actually passing the library path for the container. So the next thing is I've listed here a couple of steps and a couple of different ways to get the profile information. So for step A, if you want to get a flat profile, so flat profile tells you if you're running the TensorFlow code here, so a flat profile will tell you what are the different kernels that are being generated and how much time they consume. So the way we run is, so we are using this container, so we use Singularity exec, and so once we pass that, so we have to use the nsys command. So this actually runs within the Singularity container. So we use the command like nsys profile, and there's an option called as stats is equal to true. So we set that flag as true. So what stats tell is that you want to get the flat profile. I want to see what are the list of kernels, how much time they're taking, how many times a kernel is invoked. So you get all that information. Another parameter is where you can redirect your output to a specific file. So the output of this code will be nsys.out.qdirect. So once you pass these parameters, now it's the turn to start running your code. So you have this, the way that you launch your run the code, it's Python with the TensorFlow.py, and any associated parameters you can also pass them here. It's usually the profiling takes a lot of overhead. So we are just, in this example, we're just restricting to 5 epochs to just generate what information that we can get from running this 5 epochs of this code. And if you want to see that output, so the QD file is primarily used for the visual, the user GUI interface. But if you want to rewrite that out to a log file, so you can also redirect that. So if you want to see, okay, once we run this code, the output of this code, I've also opened this here. So if you see that it generates the entire output. So here we see that it's opening all the libraries here. So we are using the CUDA 11 here, and we're running them on a single GPU. So we are using, it also prints out what are the GPU properties, like what's the GPU ID and what information of that. And once it starts, so it opens the associated libraries required for running this code. And you see that since we're using like few epochs, so it just prints out the information. Um, Now, so the important point is, so these are all the traces that we see here. So as I said, so as we pass the option for stats is equal to true, so we want to see more information of the different kernels. So this section, starting from the line number 179, so this tells you what are the different CUDA APIs. So these are all the calls that are pertaining to you're launching a job and you're running this the training on different kernels on the CUDA device. So if you see that the last column here shows the names of the different APIs, and you see what's the total time it's taking, the number of calls, the minimum, the maximum, and the average time in nanoseconds. So we see that at least for this specific example, the launching of the kernels is adding a lot of overhead. So as you know that when this the model is running on the GPU, so once the data is processed, so then we have these kernels which are invoked and they are launched on the CUDA device, and you have these memory copies happening between the host and the device, and there is some cost associated with having these mem copies, so and also with launching the kernel. So you see that CUDA mem copy from, and also the launch kernel. So they actually are the kind of the heavy operations for CUDA API. So once we know what's the CUDA, the overall information of the APIs, So the next section will tell you in terms of the CUDA kernels that are being generated. So here from the line 226, so you see this is a report that is generated, which will tell you in a similar format. So what is the name of the kernel that's being the heaviest kernel and what percentage of time it's taking. So for example, here we see that within the CUDA DNN library, so there is specific kernel that's taking a lot of time. So this is the exact number of parameters that are being run on this for this example, and we are actually seeing there are like almost 62,000 instances of this kernel being run, and the average time and the more stats of the time consumed as well. And if you see through that, so this is kind of organized in a way where the kernels are ordered in terms of the heaviest kernels to the lightest ones. So so we see that these are the bunch of kernels which are actually generated when you're running this code, and these are kind of specific to whatever the parameters that we are passing. For example, if you are changing the batch size, for example, so we may see a different set of parameters for each of this kernel name. However, it might also vary the order of the kernels, but the algorithms should more or less be the same here. So what this captures is all the algorithms. For example, you're using all these gem routines or the kernels corresponding to the optimization libraries from QDNN and other eigenmetrics. So these are all the kernels that are being generated. So usually we see this is a pretty long list of kernels. So it's recommended that we just focus on the heavy kernels. So we know which kernels are taking a lot of time, which are the heavy kernels. So you see there are a lot of kernels that are being generated. So these are very low level information that's being generated by this profiler. So so the third section is in terms of the memory operation statistics. So this section will tell you the information on the CUDA mem copies. You are copying the data from the host to device and the device to host. So it's again a similar format. You see what are the kind of the mem copy operations here, what's the total percentage of time, and how many number of operations are being carried out here. Okay. So the first part here, the line number 371 to 375. So this will tell you in terms of the time taken. The next section will tell you in terms of the amount of data that's being passed. So in terms of the kilobytes. So whatever we are using the mem copies for the device to host and host to device transfers. And these values are aggregated across all the kernels. So there are also multiple ways to specify which operation that we want to focus on. I'll come to that in a while. So the next part is, so these are all the instructions or the profile information that is related to the CUDA APIs, the kernels, the mem copies. Now, if you were to see the operating system and the runtime level statistics, so the next section tells you that information. So here, if you see that there's a lot of time is spent where the threads are on a wait status here. So this tells us that whatever parameter that we are passing, like for example, the batch size is small enough, and there's is a lot of potential that we can actually increase that further. So predominantly, like we don't try to go through all of this because they are very fine level of details, and it may be hard to just get all, because like of too much information to consume from the profile. So it's always good to understand like what kind of information we get from using this specific tool. So I said, if you use this Insight systems, so you get information on the CUDA API overheads, what are the kernels that are generated, how much time that they're consuming, what are the mem copies in terms of the time, and also the in the message size, the data size that are being copied, and also the runtime information. So this is the information that you see from the flat profiler file. Now, say for example, if I am if I want to see the user interface. So as I said that, so we are also passing this parameter, say you want to generate this output profile, and if you want to see in a user interface format. So I've copied this file, and I also have this NVIDIA Insight Systems interface open. So I've already opened, but yeah, so what we can do is, so once you open this file, so it will generate this trace here. So the trace will tell you on a timeline basis what are the different levels of information. So for example, in this timeline view, the left side, we see that what are the operations that are running on the CUDA hardware here. So they're all grouped under one section. And they're all the threads information. So that will tell you mostly from the OS level information. So if you were to focus on the CUDA information, so we see that how this is done is like there are multiple streams where the kernels are launched on the GPU and they are running. So for example, if you see, you open this further, so we see that on the left-hand side, so these are all the kernels which are being generated, and also the percentage of time that they are consuming. So as I said, so the timeline is pretty intense. So we can actually zoom in further. So what we can do is we can highlight a specific section, and we say we want to zoom into selection. Okay. So for example, if I'm zooming it further, so I see these are the different kernels that are being launched. So after this FFT2D kernel, there is a subsequent, there's a CGEM kernel that's being run. So this timeline view is kind of similar to the tensor board profiler, but the other advantage, if you want to analyze it further, is you can actually right click and you can say that I want to see this in events in the event view. So event view is located here. So this will tell you the similar information that we have seen in the flat profile. So it will tell you what are the kernel names, when did they start, how much duration they have taken, and what GPU which we are running. So either we can also, if you want to see more finer level, like for in terms of what are the parameters or the hardware characteristics. So what we can do is, so you can also see the information here. So for example, if I'm selecting this kernel, I want to see like what are the hardware level information on this specific kernel. So you see that, so if you know what, like how CUDA runs on a GPU, so basically you have this a bunch of threads which are organized into different groups of blocks and grids. So we see that for this specific kernel, so the kernel is launched with these specific parameters, like there's a block size dimensions, and there's a grid dimensions, and how much of the memory is shared here, and also the local memory information, the shared memory information. And so one of the important points to understand here is that the occupancy value. So if you see that the occupancy value here is like 25%. So what occupancy value tells is that like how busy are the GPUs which when they're running this kernel. So ideally, so we want to have the kernels to be using maximum amount of work. So we have to keep them busy with the kernels. So if you see this information here, we see that it's currently the specific GPU running on this kernel, it's just busy only 25%. So we see that it's not heavily used. So the first, the thing that you should like consider is that what can we do from my application side to increase that the occupancy value. So we want to have the value to a larger value. So one simple way to do is to try increasing the batch size. So this example and this profile is with the I think batches of 64, I believe. So maybe you can also try running with a larger batch size, say 256 or 512, and then try to get a kind of similar metrics and similar information. Um, so you can also zoom out and maybe look at some uh, other timeline view to understand what are the other kernels and if there are any deadlocks happening. So one way to understand here is that if we find that the activity on GPUs is kind of very intermittent. Now, if we see this trace here, so we see that the GPU activity is kind of scattered here. So what this tells is that the amount of work that the GPUs are running is pretty small. So we have to increase the amount of data that has to be passed to the GPUs so that they can be busy throughout this time. So that's one of the key takeaway from this interface. Okay, so the next thing is on. So that is for the Insight systems. So in this README file, I've also put a screenshot like how does, what does the user interface look like and what kind of information that you can see from a timeline view. And if you were to further look into the details of a specific kernel. Okay, so the next one is called as Insight Compute. So what we can do is Insight Compute, as I mentioned earlier, it's kind of its way to get more details of the kernel which is running on the GPU. So this is kind of mostly focused on the GPU side of performance counters. So one way to do is if you have this SSH enabling, so you can actually you can also say you click on the kernel that you want and you say you want to analyze the kernel with compute. So that'll actually launch the compute job to do its further analysis. But as I said, so let's focus on running this using the command line version to see the information. So for using the Insight Compute, so we use the command like NCU, and it's the same thing as the Insight system. So you use NCU with the Python and you pass on your the application name and any of its parameters. Now, as I said, so if you're running this profile as is, so there's a lot of information that is being generated. So it's pretty easy to get lost in the amount of details that are being thrown to us by the profilers. So if you want to understand like how exactly can I make the best use of this tool? So so we want to understand what performance metrics we get from specific portions of the code. So for example, in this Insight Insight systems, we see the kernels called as like Ampere CGEM kernels. So we know that they actually implement some kind of matrix multiplication routines. And if you want to focus only on those kernels, so we want to say filter out the kernels which are implementing those gem routines internally. So what we can do is so we can actually pass that the specific kernels using this parameter called as kernel ID. So the Insight Compute documentation has more information on what the specific values are. But to get started with, so we can use, so we are using this the regular expression called as gem. So any kernels that have this gem in the name of the kernel, so we are just profiling only those kernels. So we don't get those like the 100+ kernels. So we want to focus only on those few kernels which are of interest to us. And we can also use different ways that if I want to get on a specific device, if you're running this job on multiple GPUs, we can also say, if you want to get the metrics only on GPU 0, so you can also pass that as a parameter here. Okay, so this is the way that you do for any general code. So going back to the script, so now if I want to run this code, the inside compute for the same example, so we see the step B here, lines 26 to 28. So what we do is we just again launch the singularity container with the image, and so after that we use this command like ncu, so that's inside compute, that's followed by your application and all the parameters for that. And so the output is you can redirect that to a file and you can view that results there. Now, as I also mentioned, like, so this gives a default picture. It kind of summarizes the high level metrics for all the kernels. Now, say if I want to focus on a specific kernel, so what we can do is, this is the step b.q. So we are using this kernel ID with regular expressions, and we want to say either we want to get all the metrics. So the metrics here are those performance counters which are exposed by the runtime libraries from Nvidia, um, and we get and we pass those similar parameters here. So a typical examples now, say if I'm running the inside compute and my application. Um, so it actually generates a lot of information into your output file. So if you want to focus on a specific kernel, so in this example, so I'm showing what metrics that we get for this Ampere SGEM 128 by 128 kernel. So this is the default information that's generated by the Nsight compute. So for with the Nsight tools, so what NVIDIA did was, so the metrics are, as I mentioned, so these are the different hardware performance counters that will tell you how good your kernel is running on the GPU. So they have classified, or they've grouped this metrics into different sections to have a very a coarse level of information that we want to get. So this section is called as GPU speed of light. So GPU speed of light will tell you a high level snapshot of what's the compute, the memory, and IO behavior of your kernel. So I think to get started, so we can just focus on this specific section. So if you run this inside compute, and in the file you want to see which kernel that we want, so we see this section called as GPU speed of light. So here, so this prints out a bunch of values. So we see what's the DRAM frequency, the shared memory frequency, what is the number of cycles that are elapsed, and we see the memory percentage here, what's the duration of the specific kernel and for that specific launch. And also this the SM percentage. So this is the how the occupancy. So how busy the kernel is when it's running on the specific GPU. So two things that we want to highlight here are the last one, that's the SM percentage. So this will tell you, as the same example as the Nsight systems. So this will tell you how busy is your GPU when it's running this kernel. And as I mentioned, we want this value to be higher. So here currently it's just consuming like 22% of the resources. And we also see like kind of the memory utilization, it's like 10%. Now, so this is the GPU, this is the kind of the summary, I would say, the section called a GPU speed of light. And if you want to dwell into more finer details, so we have other sections called as launch statistics and the occupancies from different levels of granularity. So if you're interested further, you can just go and dig down into the details of more information on the threads, the WAPs and the occupancies, the memory per block, and all that information. So basically, the way that we use these tools is you get the information and you just want to focus on where do I need to focus on and what kind of information that I'm getting from these stats and what can I do to optimize my code. Now, as I mentioned, so let's focus on the shared memory percentage here, for example. Now, if you're running the same code for two batch sizes, so here, this snapshot, okay, let me focus. So here I'm printing the same the GPU speed of light section for the same kernel with two batches. So one is using the batches 4 and one is
ELUE.
okay.
Hi,
So
Stephen Hudson, would you mind muting yourself?
Oh, sorry.
thanks. In this specific example, so we are trying to see how those values vary if you're running at two different batch sizes. So here we see this is the information that we get for batch size 4. So we see that the values for the memory percentage and the shared memory utilization percentage is here. And now we compare that against, so this right side one is showing for batches of 512. I don't know if you can see this. Okay. So if we compare this to the metrics with two different batch sizes, 4 and 512, so we see that the shared memory percentage has improved from 26.3 to all the way till 81%. So this is actually a good sign that we are improving the utilization of your on the GPU. So one of the reason here is that, so as a gem kernel is basically the matrix multiplications, it's most likely like compute bound. So if you are increasing the batch size, we'll also improve the utilization. So a lot more number of threads will be working, and they'll be running that kernel, and we're also able to see an increase in the performance as well. So that's one way that we can understand, like, you're running your profile, you're getting information. From this information, what can I do to better tune my application? So this is one specific example here. So if you were to use the user interface, it's kind of the same format. But I thought like this would be easier to just, you can focus on a specific section. You can read those what values that you are getting from running the codes. So in the script again, so you just use this specific command to generate this file. You can open the file and read, and I know it prints a lot of information, but you can just focus on a specific kernel, read through that section and see what kind of information that you're getting. And section C here is telling the same way how we use the user interface. So as I mentioned, so we just use this the command where we want to generate this the inside profile to an output file, and once you copy that to your local machine, so you can just import that QData file and have this user interface format. Okay, so are there any questions? Okay, let me see this Slack. Okay. Yeah. So one key thing that we have to remember is that profiling takes a lot of time. So we want to be more smart on how do you want to fit that scenario that we want to don't spend a lot of time just profiling. We want to maybe reduce the number of epochs for your code, and also instead of running them on all GPUs, you can just specify one GPU and get that information. Okay, so maybe next thing. Okay. So this is for the tools, the profiling tools from the Nvidia, and we're running on the Theta GPU. So next thing I will quickly touch upon is if you are running this profiling on Intel systems on Theta using Intel VTune. So this example, we are using Intel VTune to profile information using, and the example that we have used is with PyTorch. So NVIDIA one, we use TensorFlow, here we're using PyTorch. And we also have a script for running this code. So Intel VTune is kind of the same kind of methodology that we use. So it kind of uses the underlying hardware performance counters, and that will actually tell you how your code is running on the underlying CPUs. So there are multiple sections here, tools that can be used. So at a high level view, we call something called as the application performance snapshot. That's the between APS. So between APS is also it's kind of gives you a high level summary of how your code is running on the CPU. So if you want to run this job, so okay, so we just load the modules that are required here. We are running this the PyTorch code, and we're using you can use this module load vtune, and we set those library paths here. So we use APRAN to run the code on the compute nodes. So once you mentioned all those information there, so we just use this command called as APS, and that's followed by your application and any associated parameters. So APS gives you generates this file in a specific folder. And what we want to do once that is done is to generate this report. So the good thing of having this, the application performance snapshot, is that it generates the output in a clean HTML format. So for this specific example, okay, so this is the summary when we get using this APS tool. So here we see that whatever information and what platform that we are using, it also tell you how much time it's taking, what are the memory footprint, what's the time taken, what kind of limiting factors are there when running this code here. So we see that here for this specific example, the most of the time is spent on MPI already. So it's kind of bound by our MPI. So we can use further tools to analyze these, like what's taking a lot of time. And it also tells you what are the cache miss rates or from the L2 cache here. So all the stall information, and what are the IO that's happening with this code, and also in terms of the memory footprint. So this will tell you in terms of a very high level picture of is your application or your model is bound by the compute or memory or IO or any other parameter. So it's good to just get a high level glimpse of if I'm running my code, if you're training this model with different parameters, so what changes do I expect, and how does the behavior of my code run vary based on those different parameters. So APS is used for getting this high level information. And so I've also posted the snapshot here. So for this specific example, so this is the information that you see from the generated report in the HTML file. And also the vtune also has this, different sections to get more finer level of information, where you want to do this architectural exploration, where it tells you more information on the microarchitectural perspective. It exposes all those metrics and performance counters related to that. And also say, for example, here I've listed, if you want to understand what are the hotspots in my code. So what we can do is we can also use this command, -c is like you want to collect the hotspot information, and you pass that your code as a parameter there. So what is done is that, so it will run your code, and it will try to gather the information, and it will collect all the hotspots in your code. So here the methodology here is that we run this the profiling collecting part on the compute node. So if you run this code here, so all the work that happens beneath, to just you run the code and you extract information you are trying to collect the hotspot, so that runs on the compute node. And there's a next step called as the finalization phase. So finalization phase is where it tries to stitch together all the metrics, all the information that is being generated. So usually the finalization phase is not done on the compute node, so you can do it on the login node. And again, if you want to use this, the user interface, so you can also copy that report back to your local machine, and we can also use the vtune amplifier tool to import this the output report file and try to get more information from this tool. Yeah, so in this section, so I have all the scripts for running them on Theta. This is the code here. And for the Theta GPU, again, so I have the script, the Python code, and some of the information like how you can further analyze your code using the profiler tools. Okay. Let me stop sharing the screen. So do you have any questions for the Nvidia profilers or the Intel profilers? I know this is like a lot of information. It's okay. So maybe you can just use the scripts and try to get some profiles for different examples. You can use any Python codes and see what information that you're generating. And also, like, maybe have any further questions, you can also post on the Slack channel too. Okay. So Huihuo, do you want to take next?
Okay, thank you, Murali. So I will continue to share about the last part of the profiling that we want to introduce to you. Let me share my screen. Okay, so for Taylor introduced the TensorFlow profiler, and then Murali talk about the Intel profiler, Insight profiler. So all these three profiler are mostly focused on the performance of your model on a single node level, like how does the model utilize all these GPU or CPU thread placement, for example, or the kernels, how do they execute, whether it's efficient or not. So what I want to talk about is the MPI communications in the distributed deep learning. So we know that from yesterday's example, we kind of get a feeling about the scaling. Let me go back to the result that we have yesterday. So I think I put for example, Theta GPU. This is a PyTorch MLess example. So we found that from 1 GPU to 32 GPU, initially it scaled very well, but then go beyond one node, it doesn't scale that well, right? So the problem of this scaling is due to the communication overhead, since we have models on each worker, which is sitting on different GPU, but then they each of them calculate the weight and gradients. Then they have to do a synchronization, average across all the workers. Then they do the update for the next step. So this communication overhead is the problem for the scaling. So basically in this session, we want to understand, like, for example, why after going from one node to two node, what's the problem? Why there's a poor scaling here? So we will see the problem here using this profiling. So let me go back to the profiling session. So I want to just go to the MPI profiling. So this is okay. So this is the basically trying to see what are the MPI communication involved in the training. And to run this is very simple. The only thing you need to do is to export this LD preload. LD preload. This is the loading the MPI profiling library. Here we use the MPI trace. And on theta, you do the same thing. This is basically the same library. So do LD preload. So what it does, it will intercept all the MPI code and then generate the profiling result. So if you, let me also, maybe I can share my whole screen instead of share my application. Okay, so I'll just go to here, MPI, and go to the MPI folder. And then inside of this, I have the sample for theta, right? So go to the theta folder. Then you can see the submission script is essentially the same with yesterday's, except that I do the LD preload. LD preload. So this is on theta. So do the LD preload and then run the example. After that, you will see this profiling result being generated on the working directory. This is the MPI profile, and then has a number usually associated with the COBOL job ID, and then the rank ID. Here, actually, I run 2 jobs. Let me go to, we can go to one of the jobs. For example, usually I check that rank 0 have most of the information. So I can go to that. So what this MPI profiling result shows us is these are the MPI calls, and then these are the time that used, and the average pipe size. This is number of calls. So you can see that we have MPI com rank, MPI com size. This because in hover when we call the function hover init, it will initialize MPI, and then hover size, it basically will call MPI com size underneath. And hover rank will call the the MPI com rank under this in the MPI library. But then we also see the majority of the time is spent on the MPI or reduce. This is essentially trying to average all the weights and loss and gradients across all the workers. And you can see it spent like 85 seconds on the MPI or reduce. Then from here, we also see this is total communication time, so 86 seconds, and total elapsed time. Total elapsed time is the total time for running the whole job. So it says 99 seconds. This doesn't, you may be surprised that, oh, it looks like MPI communication takes majority of the time and computation take only 13 seconds. This is actually not true. In Huihuo implementation, they create a helper thread. So basically the communication and computation happened concurrently in parallel. Because they're in different layers, the computation and communication are independent from each other. So they allow us to do this overlap. So basically what I want to say is that computation is more than 13 seconds, actually more. We will see that later in another profiling. And it also show a histogram of all the codes. For example, we have broadcast. As I mentioned yesterday, when we do the MPI, when we do the distributed training, we need to make sure that the rank 0 need to broadcast the whole model to all the other ranks, so that all the other ranks also have the same starting point. Then we also can see the MPI or reduce codes, right? Different message size, from the 8 byte or reduce and to the largest here, I think is 67 megabyte, 67 megabyte. So there is a large message size or reduce. But in this particular example, we can see that the 8-byte or reduce take the majority of the time. In total, it's about 80 seconds, but then here it takes about 64 seconds. This usually is very specific to this problem. For other models, other more larger models, you may find that the time mostly spent on large message size. This 8-byte or reduce, we will see later in the timeline trace. This is from the negotiation or reduce, which I will say more later. It also shows other information like the memory footprint for each process. For example, here I think I run 128 process. So it printed out that each process, the memory footprint, it's about 1 gigabyte for each process. Okay, so this is the result. So very, very simple. I think I will just stop for a moment. You can just submit your job and then collect this MPI profiling result here. So the way to do that is just simply, by the way, do git pull first. Because I think I do some update a couple minutes ago. So go to the MPI folder and go to theta folder. Then do qsub.sh. Okay. By default, I think I specified 32 nodes. You might want to just reduce the number of nodes since we don't have that many nodes. You may just do 4 nodes. So just modify the script -n 4 so that we can all have the job running in a smaller size. Then do qsub, okay? And also I think Murali mentioned that when we do profiling, we typically reduce the workloads a little bit. Since each epoch essentially are doing similar things. So here I just only specify 5 epoch. We don't need to convert the result, right? So we using this 5 epoch, we should be able to collect enough information. So do this, do qsub, and then wait for about a couple minutes. We should be able to get this result and find out this MPI profiling result on your current directory. Okay, so I'll pause for 1 minute and let me know if you find any issues. And there's another example. Another example is on GPU. Same thing here. So in GPU, on Theta GPU, I have 2 submission scripts. One is qsub GPU. So this is basically to run the job on GPU. The other submission is run on CPU, run on the host. So because I choose device to be CPU, later on I want to say a little bit about this difference. You can just run both, you know. So even though we submitted to Theta GPU, we can still run things on just host, not offload to GPU. And we will find that it use different different communication library. So after you submit the Theta job, also go to this Theta GPU directory, submit this 2 jobs, okay? I think each of them, I set the size to be 1 node. Yeah, so it should be good. So submit both this CPU and GPU. And so I just briefly mentioned a little bit. I have a 1 line here, basically to create a symbolic link to this distributed deep learning Harvard data set. This is to solve if we have any issue on data set, because we run yesterday and suppose we get the data set on yesterday's folder. So this is just to create a symbolic link to that folder. So make sure that we don't need to download the data set again. If you find any issue with this line, simply just comment this line and then do a copy manually. Okay. And just put a message on Slack under this profiling deep learning channel if you are able to get any profiling result. Yeah, so this is basically an example you need to do. Go to theta folder, queue sub, theta GPU queue sub, and then maybe wait for that for a little bit. And this is essentially just, I put the result, I quote the result here in the README file. So you can see the theta CPU and theta GPU. In theta GPU, I put two examples there, right? One is running everything on GPU, the other is running on CPU. So that's first check on CPU on the host. So on the host, it kind of very similar to what the result we have on theta, right? It is it spends all reduced time like 100 seconds. Then of course here, because we are running in single node, so with 8 ranks, so it's a relatively smaller size. In the example I showed before on theta, it was I think 32 nodes example, so a lot larger size. So for this, within a single node, the communication is only 100 seconds. The overall time is 600 seconds or 700 seconds. So this communication is not that large. And we can also see that in this example, actually the majority of the time is spent on larger message size. It's not on 8 byte. 8 byte is relatively small. So sometimes it depends on the network or depends on the this model. Let me see if anyone. Okay, so and then want to see this GPU example. So if we upload everything to GPU, what we'll find is that, okay, it's run faster because we are running on GPU, right? So it is 49 seconds right now. On CPU, we take about 700 seconds. So this is more than 10 times faster if we run on GPU. This is reasonable. Then the other thing is, okay, the all reduce only take 6 seconds, and we only have like 2 type of all reduce. One is 4 by 8 by, right? That all this in previous example we have a lot of more larger size all reduce, right? But in GPU we only have 2 kind of size, 4 by and 8 by. The reason is that on GPU, actually we are not use MPI. We do not use MPI for doing the majority of the synchronization. Instead, we actually using the Nvidia Nico library to do the all reduce. So that's why, because the profiling library we use is the MPI profiling library. So it doesn't show up in this MPI profiling. So we will see later on using another library to see this Nico all reduce. Okay. So this is the MPI profiling. So basically just give us an understanding what are the MPI calls. The 2 important messages here is, one is that the majority of time spent on the all reduce, right? So that's for synchronizing or among all the workers. The second thing is that GPU and CPU are different, right? GPU we are allowed to use the Nico all reduce. On CPU we're using the MPI as a backend for doing the communication. Okay. So this we call the flat profiling. Basically, just put out the information for all the MPF codes. The other communication profiling is used to use the Horova building profiling feature called the Horova timeline. And again, to use it is very simple. We don't need to do too much change. Just export this environment variable called Horova timeline, and then you specify the name of the output. So this timeline.json, so what we'll get is a JSON file. So as I'm speaking, probably you can go to this directory, just submit this job, Horova timeline theta or Horova timeline theta GPU, and then you do the submission. Let me go here, check this MPI folder, so Horova timeline folder. Then can go to theta GPU, and you can check QSub. So you can just do QSub. You can specify the different number of nodes here. You can modify the different number of nodes. Then by default, I use one node. So specify this Horova timeline, and I specify the JSON file output. So, and the other thing just the same. You can, all of this just passing this environment variable like Python, pass this Horova timeline to other nodes. Suppose you are running multiple nodes. If you run single node, you don't need to do this. But if you run on multiple nodes, then we have to pass the environment variable to other nodes too. So you can just do submission, do QSub here. Then you will find that after it finish, it will produce this timeline file here. So this is JSON file, and this can be visualized by Chrome browser. So this is a timeline similar to the TensorFlow profiling timeline. We will see later. So submit this job and also submit the theta job. Again, for theta, you might want to, I specify the number of nodes to be 8 nodes. This probably is okay. Yeah, so do QSub and wait for the result here. So theta timeline JSON. Okay. Oh, it's from Nathan said that theta GPU and theta subfolder in Horova timeline don't appear to be in the Git. Oh, really? Okay, let me commit them. Sorry about that. Let me just commit that directly. Okay, I think the only thing I need to do is CQ sub here. I am on time on theta. Sometimes I cannot connect to the network. Oh. So yeah, I just push that to submission script to theta to the Horova timeline folder. So you should be able to do pull and then do the submission. Okay. Anyone get results from the MPI profiling? You can either unmute yourself or just send a message on Slack. Just let me know your progress. So as you're waiting for that result, so after finish the timeline, the NPI profiling, you can directly just visualize, check the result on Theta or Theta GPU. But for this timeline result, we need to download this file to your local machine. You can do SSH, or if you, for me, I was using Jupyter Lab. I was using Jupyter Lab. In Jupyter Lab, you can just directly do download here, your file, and then download. Choose the specific file download, whatever way you choose. Okay. After you download the file, if you want to go to the Jupyter Lab, this is the thing you can go. Okay. I'll just okay. So the way to load the data is basically you go to cron tracing. Let me put this on the Slack. Open the Chrome browser and then do cron tracing, and then you do load. Load the JSON file. For example, let me load the JSON file on Theta GPU. So I have two. Okay, there's an issue because probably because I already opened it up. So I think you just open load here. I already opened it up, so I will just check here. Okay, I have the Theta GPU timeline. This is a single node case with a GPU, and I do 10 epoch. So you can see this 10 epoch. All of these bars are from communication. Okay, so we have the buyers communication for the buyers for the weights, and it has specific number, and loss accuracy. So and then we can clearly see the number of steps here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 step, right? Of course, we see there's a slightly fluctuation for different slabs. Some epoch is different. Oh, sorry, this is epoch, not step. 10 epoch. Okay, and then we go zoom in to this to one of the epoch. The way to zoom in, we click this icon here. So there are 4 different things you can do. This is selection. This is just moving. This is for, and then you move your cursor. Yeah, there is a way. I don't know how to describe. So basically, you use, if you're using MacBook, two finger, first finger touching on the screen, stay there, and then second finger just move around, and you should be able to zoom in and zoom out. So if you zoom in this session, you can see a lot of things, right? Actually, this is a step by step. So this is step by step. So you can see these are the steps, right? There's different steps. In each epoch, we have a lot of steps. And in the MPI communication, you can see there are things called negotiate or reduce. And if we do selection, this timeline it's interesting, provided some information. If we select this, just click this, select this, and it will generate a kind of like a flat profiling. So tell us how much time is spent on this selection. So you can see negotiate or reduce 5 milliseconds. Total is 6 milliseconds, the window we selected. And you can see that the negotiate or reduce take majority of the time, right? So that's what we expect, those 8 bytes or reduce. And then the second thing we can see that this is all reduced, and under this is actually the nickel or reduce. So, and there are some overhead from other things. Basically, if I zoom if I click this again, you can see the this nickel all reduced and this all reduced. So there's some overhead from other things. So this is on GPU. It used the nickel all reduced. And again, the negotiate or reduce still take a lot of time here. And now I want to go to 4-node example. As I mentioned previously, the scaling efficiency is not that high if we go beyond 1 node. So we want to figure out what's the issue there. So this is the theta example. So this is the theta GPU for 4 node. So I still do 10 epoch. And what we found that is strangely there is a lot of time spent on the negotiate or reduce. And this occurs only at the first epoch. Later training epoch, you can see, okay, if I zoom in, move this around, okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Still 10 epoch, right? And you can see the first epoch take a lot of time due to the negotiate or reduce. And the other epoch just kind of smaller and very fast. So actually this scaling issue was caused by the first epoch. I haven't figured out why there's a large fraction of or negotiate or reduce in this at first epoch. But this is causing the issue. Okay, so suppose your model runs like hundreds or thousands of epoch, then probably this first epoch doesn't affect that too much. But if you run just several epoch and then you got converged, then this will cause a lot of issue. And so we want to see whether this is truly the case that the first epoch take a lot of time and the second and third epoch smaller fraction of the time. So I actually modify the Python code. If you do deep pool already, it's the modified version. So what I did in the code is basically I print out the time for each training epoch, for each epoch. So this is a Python, PyTorch Cypher 10 example. So what you can see is that for each epoch, I print out the time, the training time and for the testing time, right? So we can see the time spent for different epoch. And here I run like 1 node, 2 node, 4 node example. So if I do this grep as, by the way, all the results are on README. I just here just show you manually, interactively. So you can see here 1 node with 8 GPU. The first epoch still take longer time than the others, the first training, right? So the training time is 4 seconds, but then the second epoch is less than 2 seconds. Okay, but then if you go to 2 node, the first epoch becomes 23 seconds, jump a lot because of negotiate or reduce. The second epoch to the 10 epoch actually scales very well. And this is 1.6 seconds and 0.8, 0.9. So, very good scaling actually. And go to the 4 node again, we can see the first epoch still 20 something, right? Similar to the 2 node example. So that means that this first epoch this negotiate or reduce just doesn't scale at all. So that's causing the issue. The rest of that 0.4, 0.5. So still we do see the reduction of the training time there. So yeah, this is what I want to say, that through this profiling, we can figure out the problem of the scaling. Okay, I think that's all I want to say. So if you can find out the what I just said in this README. I have two README. One is followed by timeline. The other is an MPI. So because we are getting close to 3 p.m. only have 5 minutes left. So yeah, I just want to say that this profiling is very simple. You only need to do the change in environment variable and then run the same example again, right? So for the MPI, you just do the LD preload, loading this profiling library, and then it should generate this MPI profile data on your directory, which shows the MPI calls involved in this distributed training. And particularly, you can see what are the messages, what are the size message of the messages for the all reduced. And this is basically all the weights and gradients, all the tensors, the size of all the tensors in the all reduced. Second thing is the timeline. So this timeline just give us information about when does all this all reduced occur, right? And can see here. And then the other thing I didn't mention is so this is on theta, I think. Yeah, on theta. So you can see we actually have different tensors, right? Like weights and bias, and so different layers, and they do the all reduce at different time. You can see at different time stamp. So that's what I mentioned previously, that there is a communication, there is an overlap between communication and computation, because the different layers, the tensor are doing the communication at different time, and computation also different time. So there's a possibility for overlap. So here from the timeline, we can see clearly all the tensors are doing or reduce at different time. Okay. And on theta, you can see this is MPI or reduce. But on theta GPU, if we upload the communication to GPU, then it's a nickel or reduce. Okay, I think that's all I want to say. I will just pause here. If you have any questions, you can put on the Slack. I will still be available on Slack. And we probably can just conclude the session here and then come back tomorrow.